From landing astronauts on the moon to sending robotic explorers to Mars, space agencies worldwide have achieved incredible feats. Behind these missions lies a remarkable brain trust of scientists and engineers, spanning fields from astronomy and physics to biology and materials science. Their mission? To solve the unique challenges of space exploration with groundbreaking inventions. Take NASA, for example. In the 1950s and early 1960s, they pioneered the three-axis stabilization control system, enabling satellites to accurately point their antennas, instruments, and solar panels. This invention alone revolutionized satellite technology and opened the door to countless advancements. But NASA's ingenuity didn't stop there. Remarkably, about 1 in every 1,000 U.S. patents is linked to NASA's projects, underscoring their prolific problem-solving capabilities. NASA's innovations extend far beyond space. The Technology Utilization Program, a dedicated branch within the agency, focuses on translating space technology into industrial and consumer products. This means many of the conveniences we enjoy today have their origins in space exploration. Intrigued? Stay with us as we delve into the most pivotal inventions in the history of space exploration and discover how these technologies continue to shape our everyday lives. But before we continue, if you are fascinated by the incredible discoveries and spectacular wonders of the universe, be sure to subscribe to The Rocket to continue exploring the cosmos with us. Hubble Deep Field. The Hubble Deep Field, or HDF, is a fascinating image of a tiny region in the constellation Ursa Major, crafted from observations by the Hubble Space Telescope. Launched into low Earth orbit in 1990, Hubble quickly became one of the most important inventions in space exploration. It's one of the largest and most versatile space telescopes, serving as a critical research tool and a public relations superstar for astronomy. The HDF covers an area about 2.6 arc-minutes on each side, akin to viewing a tennis ball from 100 meters away, just 1/24 of the entire sky. This image was painstakingly assembled from 342 exposures taken over 10 consecutive days in December 1995. The field is so tiny that only a few stars from our Milky Way are visible. Almost all of the 3,000 objects are galaxies, some of the youngest and most distant ever observed. By revealing such young galaxies, the HDF became a landmark in studying the early universe. In 1998, Hubble turned its gaze to the southern celestial hemisphere, creating the Hubble Deep Field South. This reinforced the idea that the universe is consistent on a grand scale, a concept known as the cosmological principle. Hubble didn't stop there. It participated in the Great Observatory's Origins Deep Survey, offering a wider but shallower look at the cosmos. In 2004, it produced the Hubble Ultra Deep Field, or HUDF, the most sensitive astronomical image at visible wavelengths at the time. This record stood until 2012, when the Hubble Extreme Deep Field, or XDF, pushed our cosmic vision even further. The HDF and its successors are more than just stunning images. They're windows into the universe's infancy, allowing us to glimpse the past and understand the vast cosmos. All this from a telescope that's arguably the best multitasker in the universe. Inflatable satellites. Imagine a party balloon gone wild, a gigantic silver sphere dwarfing its creators and their trusty Plymouth station wagon in an enormous hangar. This wasn't just any balloon. It was the prototype of Echo Y, a spacecraft at a time when spacecraft usually meant something the size of a washing machine. Starting in August 1960, Echo 1 and its successors paved the way for modern space-based telecommunications using technology dating back to the 18th century. This 100-foot sphere, tested in 1959, wasn't the actual Echo Y, but an experimental version. It had a volume of over 500,000 cubic feet and, if laid flat, could cover more than 30,000 square feet. The Great Balloon was designed to reflect radio signals from one point on Earth to another, a groundbreaking achievement for artificial satellites. Echo I wasn't the end of inflatable satellites. Echo 2 followed, and during the 1960s, 4 more were launched to gather atmospheric data. In 1966, PAGEOS, short for Passive Geodetic Earth Orbiting Satellite, helped the U.S. Coastal and Geodetic Survey pinpoint global reference points with precision, aiding in the creation of accurate maps, measuring Earth's dimensions, and verifying continental drift theories. Even today, inflatable satellites are used for everything from space stations to telescopes. When a big thing needs to fit into a small package, inflatables are a top choice. The ECHO project's most significant scientific discovery was unintentional. The Holmdel antenna, set to capture ECHO's faint signals, kept detecting a mysterious static. Radio astronomers Arno Penzias and Robert Wilson, after investigating every potential cause, found that the antenna was picking up blackbody radiation, evidence of the Big Bang. ECHO had accidentally helped confirm the universe's primordial birth. In the grand tapestry of space exploration, the development of inflatable satellites stands as a testament to human ingenuity and adaptability. These remarkable inventions, with their compact design and versatile deployment capabilities, have significantly expanded our reach into the cosmos. By providing a cost-effective and efficient means of deploying satellites into space, inflatable satellites have revolutionized how we conduct scientific research, monitor Earth's environment, and communicate across vast distances. Spacecraft commands. One of the most critical inventions in the history of space exploration is the development of spacecraft command languages. These specialized computer languages are designed to manage spacecraft mission systems, allowing for precise control over spacecraft operations. A spacecraft command language, sometimes referred to as a satellite control language or systems test and operation language or STOL, is used to send instructions or telecommands to spacecraft. These languages are not just for commanding remote spacecraft. They play a crucial role in the development and verification of onboard systems like prototypes, engineering models, flight hardware and software, and ground systems prior to launch. Unlike telecommand protocols, which are usually in binary format, spacecraft command languages are written in a way that resembles human languages. This makes them more user-friendly and accessible. Some languages, such as the spacecraft command language or plan execution interchange language, can even be executed directly on the spacecraft by an onboard executive, enhancing their functionality. One notable example of a spacecraft command language is NASA's Systems Test and Operation Language, developed in 1978 by the Goddard Space Flight Center. STOL allows users to communicate with payloads, applications, programs, and other ground system elements. By interpreting high-level language directives, STOL enables the execution of programs, printing of data, and sending of payload commands. The significance of STOL and similar languages in space exploration cannot be overstated. They automate repetitive tasks, ensuring that fixed sequences of operations are performed consistently and accurately. This repeatability is crucial for the reliability of test procedures and operations at the Project Operations Control Center. By guaranteeing that each step is executed correctly every time, these languages minimize the risk of errors, enhancing the overall reliability and success of space missions. In the broader context of space exploration, the development of spacecraft command languages represents a leap forward in our ability to manage complex missions. They have enabled us to undertake sophisticated projects with greater precision and reliability, making them one of the most important inventions in the history of space exploration. Soyuz Reentry. In the realm of space exploration, the Reentry Capsule of the Soyuz spacecraft stands out as a marvel of engineering, ensuring the safe return of cosmonauts from their journeys in space. Known by its Russian acronym SA for Spuskymi Apparat or Descent Apparatus, this capsule is the only section of the Soyuz vehicle that returns to Earth at the end of a mission. Crafted from durable aluminum alloy and coated with ablative thermal protection, The ball-shaped descent module of the Soyuz capsule is designed to withstand the intense heat of re-entry. Its front bulkhead and main heat shield, crucial for protecting the crew, are constructed from a robust titanium alloy. Inside the descent module, cosmonauts recline on personally contoured couches during ascent, descent, and landing. These seats have face controls and displays developed by OAO Phasotron NIIR, facilitating critical flight activities throughout the mission. Packed within the re-entry capsule are life support systems, batteries, parachutes, and solid propellant engines for a safe landing. 8 small attitude control thrusters, fueled by hydrogen peroxide, ensure precise orientation during descent. However, the degradation of peroxide over time limits Soyuz missions to around 6 months. An independent guidance, navigation, and control system guides the capsule during descent, providing a simpler alternative to the main flight control system. A periscope extends from the descent module, offering the pilot a forward view of the docking mechanism and a downward view to track Earth's surface. Critical to maintaining a comfortable environment inside the capsule is the ventilation hardware, which regulates temperature and air circulation across the 3 pressurized compartments. This system operates not only in space but also during pre-launch processing, on the launch pad, and after the completion of the flight on land or at sea. In essence, the Soyuz re-entry capsule embodies the pinnacle of space capsule design, blending cutting-edge technology with reliability to ensure the safe return of cosmonauts from their voyages into the cosmos. Apollo 1. Apollo 1, initially designated AS-204, was poised to mark a historic milestone in the American space program as the first crewed mission of the Apollo program, a crucial step towards landing the first man on the moon. Scheduled for liftoff on February 21, 1967, it aimed to conduct the first low-Earth orbital test of the Apollo Command and Service Module. However, tragedy struck during a launch rehearsal test at Cape Kennedy Air Force Station Launch Complex 34 on January 27th. A cabin fire erupted during the test, claiming the lives of all 3 crew members, Command Pilot Gus Grissom, Senior Pilot Ed White, and Pilot Roger B. Chaffee. In the aftermath of the fire, NASA initiated an intensive investigation to determine its cause. Both chambers of the United States Congress also conducted inquiries to oversee NASA's investigation. The Apollo 1 disaster prompted soul-searching within NASA. Gene Kranz, addressing his team in mission control, acknowledged the program's shortcomings and emphasized the imperatives of vigilance and competence. His speech underscored the unforgiving nature of space exploration and demanded nothing short of perfection from every member of the team. Following the tragedy, the Apollo program underwent an extensive review and redesign. It was discovered that the command module was not only hazardous, but also, in some instances, carelessly assembled. This revelation prompted a shift in approach. The remaining Block 1 spacecraft were designated for uncrewed Saturn V test flights, while all crewed missions would employ the redesigned Block 2 spacecraft. These changes culminated in the creation of Apollo 11, the 11th iteration of the program. This mission, launched in 1969, marked the triumphant culmination of the space race as it achieved humanity's long-cherished dream of landing on the moon. The legacy of Apollo 1 lives on as a poignant reminder of the sacrifices made in the pursuit of space exploration and the resilience of the human spirit in the face of adversity. Space Lab Electron. The Space Lab Electron, developed by Rocket Lab, stands as a pivotal invention in the history of space exploration, catering to the burgeoning commercial small satellite launch market. This 2-stage, partially reusable orbital launch vehicle boasts several groundbreaking features, including its innovative Rutherford engines, the first electric pump-fed engines to power an orbital-class rocket. Since its maiden flight in May 2017, Electron has become a prominent player in the space launch arena with an impressive track record. As of May 2024, it ranks as the third most launched small-lift launch vehicle in history, having completed a remarkable 46 launches. One of Electron's notable achievements is its capability to launch payloads weighing between 200 and 300 kilograms into a sun-synchronous orbit of 500 kilometers. This makes it an ideal choice for deploying CubeSats and other small payloads into space. Rocket Lab's commitment to innovation is evident in its efforts towards reusability. While initially designed as an expendable rocket, Rocket Lab has successfully recovered the first stage of Electron twice and is actively working towards achieving full reusability, an ambitious endeavor that could revolutionize the economics of space launch. Moreover, Electron's versatility is enhanced by its compatibility with a kick-stage or Rocket Lab's Photon spacecraft, providing customers with flexible options for payload deployment. Rocket Lab's dedication to meeting customer needs is further demonstrated by its streamlined launch services. Customers have the option to encapsulate their spacecraft in payload fairings provided by Rocket Lab, simplifying the pre-launch process. The Lab Electron represents a transformative invention that has reshaped the landscape of space exploration, enabling commercial entities and research institutions alike to access space with unprecedented ease and affordability. Its pioneering technology and commitment to innovation continue to propel humanity's quest for knowledge and exploration beyond Earth's boundaries. As we contemplate the myriad advancements in space exploration, from the revolutionary Electron launch vehicle to the tragic yet transformative lessons learned from Apollo 1, we're confronted with the profound mysteries that continue to intrigue us about the cosmos. With each technological leap forward, we inch closer to unraveling the secrets of our universe. But amidst the awe-inspiring progress, one question persists. What new horizons await us, and how will these innovations redefine our cosmic journey?